So now we'll talk about what are forces. So in classical mechanics, an object with known physical properties is placed on any initial location moving with an initial velocity. We know, or we can measure, all of the interactions of this object with its environment, that is, all of the objects that are surrounding it. And we can predict the subsequent motion of that object. That is, we can predict its position and velocity at all future times. So basically, the classical problem is find x as a function of t and then calculate velocity and acceleration known from it. In general, we can generalize this by a three-dimensional vector having components x, y, and z, as we talked about in the last chapter. So what is force? The interaction of a body with its environment is described in terms of force, which is denoted by F. All human activity involves forces in some means or another. You just sitting on this chair involves forces. A force can be described as a push or a pull in a certain direction, which means if it is a push or a pull and it has a direction associated with it, then it has to be a vector quantity. So forces are described by using vectors. For every force, we must specify a direction on which it acts, and the forces have to be combined by using the rules of vector additions. Head to tail rule, for example. Now, what is the cause of a force? Each force exerted on an object is caused by a particular body in its environment. For example, pushing force on the crate by a worker, the frictional force on the crate by the floor, or gravitational force on the crate by the earth. So, when analyzing forces in a problem, please be very careful to describe each force on which acts on the body and the body in the environment that is responsible for the force. So how can a force be measured? Well, one simple way of doing this is by a spring scale. By hanging the masses on a spring, we find that the stretch of the spring is proportional to the applied force. So as you keep increasing the mass more and more, the spring will stretch more and more. Another important thing to remember is that the SI units of force are newtons. We will talk about this again. Net force. The net force is the vector sum of all the forces that are acting on the body. So for example, net force can be all of the different kinds of forces that are acting on it. For example, while you're sitting here, force of gravity is acting on it. There's friction present between you and the chair that you're sitting in, and so on and so forth. So now let's do an example. Forces on an airplane in flight heading east are as follows. Gravity 16 kilonewtons, lift 16 kilonewtons, thrust 1.8 kilonewtons, and drag 0.8 kilonewtons. What is the net force on the plane? So now this problem says that there is a plane and it is heading eastward. Okay, so it's going towards the east. And on that plane, there are different forces that are acting on it. So gravity, we know, always acts downwards. So F of G always points downwards. Then it says it has a lift. If it's a lift, then that means it is going to be pulling it upwards. So a lift pulling it upwards, let's call it F lift. Okay? And then it has a thrust that's making it go forward. So the thrust is going to be F thrust, pushing it outwards, and then the drag, which is making it go backwards, and I'm just going to call it D for drag. Okay, so what is the net force on the plane? So all of the forces that are acting on it are these ones. Now note what is going to happen. I now have to find sigma F, which is sigma F net, right? Which now, if you notice, is in terms of its components. So sigma F net will be Fx squared plus Fy squared. Sigma, and I forgot sigma, square root, right? Okay, now what is Fx squared? What is Fx squared? Well, my sigma Fx is all the forces acting along the x-axis. So if I was to redefine my coordinate system, I could call this x and call this y. And I could say sigma Fx is actually equals to all the forces that are directed towards the positive x-axis, I am going to call them positive. All the ones that are pointing towards the negative side, I'm going to call them negative. Okay, so first of all, write down all the forces that are acting along the x direction. Okay, then all the forces that are acting along the y direction. So this is going to be F lift and Fg. Okay, now this is your chosen coordinate system, right? So if this is your chosen coordinate system, this means this is going to be your plus, because it is along the positive x-axis. This is going to be minus because it's along the minus axis. This is going to be plus, and this is going to be minus. Okay? So this gives me sigma Fx in terms of all of their forces. So now all I need to do is plug in numbers. So for example, F thrust, it gives me is 1.8 Newton, 1.8 kilonewtons, minus drag, it gives me is 0.8 kilonewtons. Similarly, my FL, which is my lift force, is 16 kilonewtons. And my force of gravity that's acting on it is also 16 kilonewtons. So if I solve it, I get 0 newtons here and 1 kilonewton here. Okay? That means my F net is going to be equal to 1 squared plus 0 squared square root. And my answer is 1 kilonewton. So the net force that's acting on this plane is 1 kilonewton. Okay? So are we done? Remember, force is a vector. What does that mean? If force is a vector, this only gave me the magnitude of the net force. What else do I need? Yes, absolutely. I still need a direction that's associated with it. So what do? In order to calculate a direction, I go back to my prior information, Fy over Fx, which gives me Fy, which was equals to tangent inverse of 0 divided by 1 kilonewton gives me tangent inverse of 0, and tangent inverse of 0 is theta equals 0 degrees. Now what does that mean? Remember when we were talking in chapter 2 about the angles? What angle is 0 degrees? So it starts from this reference line. So my 0 degrees is this one. So this point east, as it should be.